Thanks. So, yes, I'm going to talk about, moving mask hypothesis or approximation to select physically relevant microstructures. And whereby microstructures, I mean microstructures arising in martensitic phase transformations. As you have heard right before, martensitic phase transformations are transformation from a solid state to a solid state. And they consist in an abrupt change in the crystalline structure occurring in certain alloys or ceramics when the temperature is moved across the threshold. So above the critical temperature, we usually have a high temperature phase which is called austenite, and which in most applications is a cubic lattice, while below the critical temperature we have a lower symmetry phase which is called martensite, and at the critical temperature, at least theoretically, we have a change in the lattice structure from the austenite to the martensite. As you can see in this example, we are considering a tetragonal lattice for martensite, and there are three different ways to deform a cube into a tetragonal lattice, and this gives rise to three different variants of martensite. So we call the variants of martensite the possible different lattices that are obtained by stretching our cube in different ways. So what is interesting is that this type of the multiplicity of variants of martensite can give rise to important applications as the shape memory effect, which is the ability of certain alloys to recover deformations which are apparently plastic on heat. So for example, you bend a fork, you heat it up, and the fork goes back in its previous shape. But also mathematically they are interesting, or physically they are interesting, because they give rise to very interesting patterns or microstructures that you have seen already before. So in this case we have austenite, which is the high temperature phase on the right hand side of this plane, and we have two different variants of martensite which are rapidly twinned or very closely twinned on the left hand side of this interface. And however, the microstructures don't really are not always so simple and somehow symmetric or clear, but can be very complex and very much more difficult to describe and understand, as in the case of zinc and gold copper that was mentioned in the previous talk, or also in this other material by Tomonari and Amura, where we see a single crystal, and at every color, both here and here, corresponds a different martensitic variant. So the idea of my talk, the aim, would be try to find a common characterization of all these different microstructures, which apparently have nothing in common a priori. But somehow, in a first approximation, neglecting some small elastic and plastic deformations, have something in common. At least that's my claim. So in order to do this, let me start by explaining some mathematical theory to describe these martensitic phase transformations. So the idea is to, one approach is to model these transformations in the context of continuum mechanics. So one considers omega to be the region occupied by a sample in its austenite phase right above the critical temperature. And then we look for a map Y that gives us the position of the points in omega after the transformation has occurred and the whole sample has undergone a martensitic phase transformation. So since Y is mapping R3 to R3, its gradient is a 3×3 matrix, and locally at almost every point is supposed to give us the matrix that deforms the cubic lattice, the austenite lattice, in the martensite lattice. And as you can see in this easy picture, even we can have a discontinuous gradient, so have two different variants of martensite which are somehow next to each other, but by keeping the continuity of the deformation, by preserving the continuity, the Lipschitz continuity of the deformation. And following the approach of Ball and James, we can ask or frame the problem in the context of nonlinear elasticity and ask that the map Y minimizes a certain energy functional. So the energy functional must reflect the phase transformation. So above the critical temperature, the energy density must prefer austenite, while below the critical temperature, the energy must, the martensite must be energetically preferable. And at the critical temperature, all phases are energetically equivalent. Let me point out that here in this schematic picture, here the one is the identity matrix, which represents austenite, and this U1, UN represent the n different variants of martensite. So, for example, in this case, in the case of this zinc and gold copper alloy, the transformation is from a cubic to a monoclinic lattice, and there are 12 different ways to deform a cubic lattice into a monoclinic lattice, and these are given by these 12 matrices. So the idea is that on top of this, we have to add SO3 in front of every energy well, and this is to preserve framing difference. That means if we rotate our body from an elastic point of view, there's no added energy in it. So as you can see from this schematic picture, the energy is not quasi-convex, so it's not weakly lower semi-continuous, and a priori minimizers do not exist. Depending on the boundary conditions, however, with the technique of convex integration, one can show that infinitely many minimizers may exist. And once you have infinitely many minimizers, the model can fail to be predictive somehow, because the question is, do we observe in the physics infinitely many minimizers? Yes, no, and if yes, are all the minimizers that we can construct with this convex integration technique physically relevant, or there are some that are not? So the usual approach to cope with this problem somehow is to try to endow the model, add to the model some further information which gives us more insight into the physics. And the easiest approach that is followed in the literature is to add some interfacial energy. Indeed, as Dick was saying before, interfacial energy plays a role in this finite scale of this twinning. So somehow the interfacial energy is related to the scale of this finely oscillating martensite variance. So in this case, the question that arises would be, if we consider a regularized problem, which is more physically relevant and that keeps in account this interfacial energy, can we somehow select the minimizers of the non-regularized problem? Can we somehow use this regularization to understand better the original problem? And the question is extremely complicated, and the answers in the literature are just partial. So, for example, there are work by Conti, Fonseca and Leoni, or Conti and Schweitzer, which study the gamma limit of the energy just in the case of two wells, but under simplifying assumptions. The problem is that they don't keep in account boundary conditions, and without boundary conditions, there's no force that causes fine oscillations of the microstructure. So this is not somehow the result is not really relevant to the question I was asking. There's a different approach somehow a different approach to the problem, followed by Ruland, Zillinger, and Zwicknagel, about which Ankana will talk later in her talk, but still does not give a real answer to the question whether we can select minimizers of this of the previous problem. And I try to join the crowd as well by studying this simple model problem, and in this case we can show that the interfacial energy selects minimizing sequences. However, this is not the physical case, so still it's not relevant. However, what I claim is that interfacial energy often in applications plays just a marginal role. Sorry. Sure. Sorry. Thank you. So if you were sleeping, I'm sorry. Now you'll wake up. So yeah, what I was saying is that I claim that this interfacial energy is useful to select somehow physically relevant microstructures, but in some cases is not. And I claim that in this case is not. For example, in the case of this zinc and gold copper alloy. Indeed, as was mentioned in Dick's talk, this material closely satisfies these cofactor conditions CC1 to 3, and so I don't want to enter again into what these special conditions are, but the claim is that thanks to these special conditions, as was mentioned before, this material can form exact interfaces between laminates and of martensite and austenite without any interfacial energy. So there's no force asking for fine twinning, and so a priori we could see an evolution which is just a single variant of martensite propagating into the sample. So my claim is that if interfacial energy was the main effect to select physically, the main ingredient to select physically relevant microstructures, this would not be the picture we observe in experiments. So somehow there's something else that takes place or which influences the microstructure that we see, and I think, or somehow the approach that I will follow is to try to understand how dynamics work. So this is I will show you now the experiment of how this phase transformation takes place. So we have high temperature phase. When we see all blue is the austenite phase, then the material is cooled down and we see a microstructure of martensite. Every different color corresponds to a different variant of martensite. And what we see is that by cycling many times, every time we see a different microstructure, a completely different microstructure. So somehow the problem is mathematically extremely ill-posed, because whatever type of model you can try to introduce to predict the microstructures, there's no possibility to have any stability result or uniqueness result of the microstructures, because this is not what we observe experimentally. So
if they do a really careful experiment, can they reproduce it if they heat it carefully and slowly?
You can ask to Sherry, she has done many experiments, but
can you repeat it if you get through the heating very carefully and slowly?
No.
Never?
Cannot.
Never?
Yeah, we did like very careful temperature gradient,
Yeah.
like uniaxial temperature gradient, so that the heat flows in this direction, but every time it forms completely different.
Okay. All right, thank you.
sorry. Okay, so yeah, the point is that, as I was saying, mathematically then it's very difficult to introduce a system of partial differential equations or whatever model and then be able to predict this. So somehow we have to get some collective behavior or get through some other idea. And the idea that somehow I will follow during the rest of the talk is to follow the intuition that it looks as if there was a moving curtain or a moving mask which covers and uncovers at every thermal cycle a different microstructure. So it seems somehow that there's very little changes in the microstructure after this have been uncovered by this curtain or this this moving mask. So let me first try to make try to transform this into an easy idea. Let's see whether I'm able to do this. But somehow what we have is we consider a domain omega, and we'll have this. We'll divide this in two different regions: omega A, where we have austenite, and omega M, where we have martensite. And then we have an interface, or more complex, more multiple interfaces evolving in time. And what we assume is that the martensite domain is expanding. And what we also assume is that for almost every point in the domain, there will be an instant in time when the interface is passing through the point. So not here, but this is the instant in time when the interface passes through the point. And so following this we can try to transform this requirement in formulas. As I was saying, the first hypothesis is to say we consider two different regions one occupied by austenite, one occupied by martensite, and we can assume that austenite or martensite is expanding somehow or shrinking. We will, without loss of generality, you can assume that austenite is shrinking, and we assume that for almost every x there exists a time when the interface passes through this point. And finally, this last assumption here is to say that the microstructure does not change after it has been uncovered by the moving mask, by the moving curtain. So there is no real relaxation or changes in the microstructures after the phase transformation has happened. That is quite similar somehow, or a good approximation, seems a good approximation of what we observe mathematically in the experiments. But let me point out that the same moving mask idea can somehow be applied also to other martensitic phase transformation. For example, in this experiment in nickel magnesium gallium, if we consider average deformation gradient, so somehow a deformation gradient which is an average of what happens, for example, at the scale of this yellow ball. And again, what we observe is a similar moving mask idea, where we have these two domains and this interface moving, and except for this somehow smaller relaxation of the twinning given by the interfacial energy effects, we still have this moving mask it seems that the moving mask approximation is somehow true. And finally, let me show you a last situation where the phase transformation still looks very different from the two previous one that I've showed you, but where somehow in a first approximation the moving mask hypothesis seems to hold as well. So this is an experiment by Tomonari Namura, and this material is similar to the very complex, to the one about which I've shown the complex microstructure at the beginning. But you see there are different variants of martensite nucleating in different points of the domain and expanding, but somehow there's no real change in the microstructure at in these islands of martensite. And however, what we are sure is that here at these junctions there are some plastic or elastic effects which should be taken in account. So the moving mask hypothesis maybe here is not really reliable. But on overall, in a first approximation, we can identify this. We can somehow apply this also to this case. So let me start with the first simple case. We assume that the interface propagating between austenite and martensite is a plane, and we assume that on one side of the plane we have a microstructure of martensite, and on the other side we have austenite. And when we let this interface move and cross all through the domain, in the end what we can deduce, what we can prove, is that the gradient, the microstructure described by this deformation gradient, should be of the form identity plus A tensor n, where A can depend on the space. So somehow this gives a strong constraint on the possible deformation gradients that can arise from a martensitic phase transformation satisfying this moving mask approximation. But as I was saying, we can generalize this to more complex interfaces. So we say that our microstructure satisfies, or our deformation gradient representing a microstructure satisfies a regular moving mask approximation if it satisfies a moving mask approximation, and on top the interfaces given by what is not in austenite and not in martensite satisfy this further condition. That means that the set of good points that I will tell you about in a second has full measure. So almost every point is a good point. What do I mean by a good point? So good point means first that there exists a time when the interface passes through the point. Second point is that the interface contains a Lipschitz graph which is differentiable at the point. And third, that the interface separates at the point of austenite from martensite. So let me talk by examples. So these blue points, 1, 2, 3, 4, they are good points. Why? Because in all these points, the interface is separating austenite from martensite, and even if here there are two different interfaces collapsing onto each other, the interface contains a Lipschitz graph which is differentiable at that point. This is not true, so bad points, not good points, are these green points. Why? This one because the interface at that point does not contain a Lipschitz graph which is differentiable at that point, because here the interface has a singularity, and here because the interface does not separate austenite from martensite, but is just in between austenite. And this somehow, however, allows us to include the nucleations at the interior of austenite, because this interface then can propagate, and somehow we can include in this model also nucleations occurring at the interior of austenite. Okay, and what can we prove again is that if we assume that a map Z satisfies the regular moving mask approximation, then there exist two bounded measurable vector fields such that gradient of Z is equal to identity plus A tensor n, which is again a strong constraint on the possible microstructures that we can observe. And why it is a strong, the fact that it is a strong constraint, I will talk about this a bit later. Before, let me mention that some sort of converse of the theorem can be proved, and it's, let's suppose that we have a map whose deformation gradient is of the form identity plus A tensor n, and suppose further that the image of Z minus the identity map is contained in the image of an absolutely continuous simple curve of finite length, and I will go through this hypothesis in a second. Then somehow we can say that this deformation gradient satisfies a regular moving mask hypothesis. What does this mean? This means that once we have a deformation gradient of this type, we can reconstruct where the phase interfaces were during the phase transition. Okay? So somehow this is a powerful tool, because we said from the phase interfaces we can construct, we can understand the deformation gradient, and from the deformation gradient we can reconstruct the interfaces. Let me just say that this assumption on the image of Z, so the map Z minus the identity has gradient which is a rank 1 map. So somehow is if Z was smooth, locally would be a one-dimensional curve. This is not always true in case of just a Lipschitz map, but clearly the theorem can be generalized to union of absolutely continuous curves under reasonable assumptions. And okay, given that, let me mention, let me try to tell you why this differential constraint somehow is restricting the possible microstructures. So let me consider 4 martensitic variants, U1, U2, U3, U4, which are 4 out of the 12 possible variants that you have in zinc and gold copper. And let me assume also that this parameter D, which is a parameter of the lattice deformation, can be measured, and in zinc and gold copper is different from 1, and so we can assume it's physically relevant to assume that D is different from 1, and we assume that our gradient of Y, which represents an average microstructure, is an average microstructure constructed with these 4 deformation gradients. So we can mix in the way we like these 4 deformation gradients and construct a microstructure, and we ask that the microstructure satisfies this further differential constraint, and what we can say is that then our microstructure must be on average constant. So the gradient of Y must be constant. So somehow we are able to prove a strong rigidity theorem thanks to this further differential constraint.
The QC is that quasi-convex hull?
Yes, QC is the quasi-convex hull. So this set here means that these are the all possible microstructures that you can obtain by finely mixing these 4 martensitic variants. And what we can take this theorem somehow to a next level and say that take two different martensitic variants U and V, and we assume that they do not fulfill the cofactor conditions. So we assume that we take two martensitic variants, we mix them, we construct a microstructure, but this does not satisfy the cofactor conditions, so the conditions that I was mentioning before and that Dick was mentioning before. So whatever martensitic microstructure with these two variants, which satisfies our differential constraint, then it must be on average constant. So again, convex integration here could give you many possible microstructures that you can obtain, but thanks to this differential constraint that we obtain thanks to our moving mask hypothesis, we can deduce that if the cofactor conditions are not satisfied, then two martensitic variants can form just a constant deformation gradient, so an average constant microstructure. And I like this result quite a lot, because somehow one can also be more precise and show that when the cofactor conditions are satisfied, you have exactly 1 degree of freedom, so you can vary the volume fraction exactly in this direction m. So and what does this tell us is that these cofactor conditions are important not only because they allow to change to have an interface with austenite without an interface layer, but also that they can vary. They have a degree of freedom. They can vary the volume fractions by still being compatible with austenite. So somehow gives they also give flexibility in the satisfaction of this differential constraint. So just let me mention that under some regularity assumption on A and N, and the fact that one requires that the vector n does not jump across the interfaces, one can prove that the divergence of A is equal to 0 in a distributional sense. But before concluding, let me ask or answer the following question. So we have introduced a moving mask approximation, and we have said that this provides a constraint to the microstructures. So going back to the experiments in zinc and gold copper, the question is, can we construct in zinc and gold copper microstructures that are extremely complex, or pictures that are so colorful, by satisfying this differential constraint? So the answer a priori would be no. But in the case of zinc and gold copper, somehow it turns out that this material satisfies not only the cofactor conditions, but some further compatibility between phases, somehow that makes this construction possible and quite easy. So just to give a flavor of what that means, it means that in this further compatibility condition in zinc and gold copper, we can take 6 variants of martensite, so related to these 6 deformation gradients, and all these 6 deformation gradients are rank 1 connected to the identity, so they satisfy this differential constraint here. And when we mix them, they still satisfy this differential constraint. And we can mix different type of this kind of laminates together and somehow produce even more complex microstructures. And here, let me mention that n alpha, n beta, and n gamma are not do not lie in the same plane. So somehow one can also construct three-dimensionally curved interfaces which evolve and at the same time satisfy this differential constraint that I was telling you about. So to conclude, let me say that we have introduced a moving mask approximation, which is based on an experimental observation on the dynamics of martensitic on evolution in martensitic transformations, and this can also be framed in the context of dynamics of continuum mechanics. However, as you can easily expect, this framing is not fully rigorous by the moment. And what this moving mask approximation allows us to do is to restrict the possible deformation, the set of possible microstructures that we can observe, to a subset that satisfies this differential constraint that I was. That means that the deformation gradient is equal to identity plus A tensor n. what we can also show is that the moving mass approximation still allows to represent the complex microstructures in zinc and gold copper. So it's restricting our deformation gradient, but still allows us to represent the infinitely many microstructures that we observe experimentally. And finally, let me mention that some experiments conducted by Sherry show that this number, which is the norm of the cofactor matrix of identity minus grad y, is of the order of 10 minus 4 in this zinc and gold copper alloy, and somehow this seems to confirm this number is 0 if and only if gradient of y is of this form. So somehow the fact that this number is small seems to confirm that this constraint is true, at least is close to be true in this material, and seems so to confirm to the validity of the moving mass approximation. Okay, thank you for your attention.
Yeah, so thanks for many interesting thoughts. Mathematically, the cofactors are never exactly equal 1, and even 10 to the minus 4 is not exactly 0. Would it be possible to include deviations from this in, say, in a perturbation theory sense, and to include information about that in your framework?
So I guess so. The problem is like always that the more your model becomes accurate, the less you can say predict hand and paper. But I think somehow this if you look at this very complex microstructure somehow, you just see 12 colors here, and you can measure them, and you can see that there are 12 deformation gradients, and which are exactly close to be of this form here. They are not exactly like this, but they are very close to be like this. However, so if you consider the problem of trying to you impose that the grain does not deform during the phase transformation, the shape of the grain doesn't change, and you consider just 12 deformation gradients, okay, the ones that are given by this formula, and you can just show they are 12, then you can prove that no such microstructure is possible. So we see that also there are some of these two different variants which match somehow on a small plate, and there for sure you have elastic deformations which are exactly taking place. So the idea is that this is somehow a first step to try to justify the fact that we can consider gradients or deformation gradients which are close to this identity plus A tensor n. But clearly when you go through really understanding, then I mean no such thing exists as satisfying perfectly the cofactor condition. But yeah, I don't know anything. Maybe somebody knows about trying to understand how to quantify errors or elastic deformations in these martensitic transformations. But
in case you don't have rigidity, so cofactor condition is satisfied, can you say something about geometric properties of the moving interface, perhaps a curvature or emission?
Sure. I mean, so we are if we consider simply the two martensitic variance case, then you can, as I was saying, if you satisfy this constraint here, and if you are a laminate, so you construct with just two martensitic variants, you are, and you can go back to construct the interfaces, provided that you have that your image lies in a one-dimensional curve of finite length, which is, and in this case, it turns out that when you when you satisfy the cofactor conditions, the freedom you have is a one-dimensional parameter, and the image is exactly a one-dimensional curve. So from there, you can use the theorem we were using at the beginning and somehow find explicitly the parametrization of the interfaces. But in the case of type 2 twins, they are always planes. While in the case of type 1 twins, they are curved surfaces, but somehow always lying in this plane, which is generated by OA, OB, and M, which are in the same, all coplanar.
Why did you say in the Inamura picture that microstructure was not sort of, or the ideal microstructure was not theoretically possible? I didn't understand.
I mean, I've done some computation somehow, and I've tried to see whether I was able to match these identity boundary conditions by just using 12 deformation gradients of the form identity plus A tensor n. And this turns out not to be possible. So if you take the quasi-convex hull of the set generated by these 12 matrices, it does not contain the identity. So there's no, so the point is, I think, and I think you can show that there exists a neighborhood of these 12 matrices of small size epsilon, such that the identity does not lie in the quasi-convex hull of this, of the set generated by this 12. So somehow you have to take.
Why does it have to match the identity on the boundary of the grid?
So I think this was coming from a discussion with you that was saying that I'm not that was saying that somehow different the experiment here is quenched. So the sample is thrown, the hot sample is thrown in some cold water, and this grain is surrounded by other grains, as far as I understand the experiments. I'm sorry if this is not completely accurate, but somehow there's no time for this internal grain to change shape, since they're also the constraint imposed by other deforming grains around. I'm not sure whether this is.
But identity is in the quasi-convex hull if and only if the determinant of the transformation stretch matrix is 1, right? That's
You mean the dilatation technique, I think.
what's that?
He probably means the dilatation corresponding to the corresponding.
Do you mean
to
really the
transformation.
identity, or you mean a dilatation?
No, I think it is
Or should we-
the identity, but you're considering a finite set of matrices, 12 matrices, and they
Oh, I see.
so you're not considering wells, you're considering
Okay.
12 matrices, which are the 12 martensitic 12 plates that are compatible with identity somehow.
Good, thank you, Francesco, again.